So on Wednesday of last week, we were done with the first lesson of the unit, which dealt with simplifying radicals, basically. I know everybody that in the first lesson, we had to write entire radicals as mixed radicals and mixed radicals as entire radicals, and we had variables in there. But what I want us to focus on is the fact that whenever you have a radical, it needs to be simplified. Forget about everything else. You see root 20, you need to simplify that. So if you see root 20, if you're like me, you see 4 times 5 giving you 20, and that means that since the square root of 4 is exactly 2, root 20 is exactly the same as 2 root 5. Some of you may prefer to take 20 and break it into 2 times 10, and then break the 10 into 2 times 5, and then say I have a pair of 2's that can come out as a single 2, and I have root 5 left over. I don't frankly care which method you use. What I care is that you know root 20 can be written as 2 root 5, and you can get there. It shouldn't be a big Herculean task. It takes you a couple of seconds to think about it, and then you write it. Okay. So what we did on Wednesday was we were multiplying radicals. And when you multiply radicals, you multiply coefficients by coefficients and radicands by radicands. So for example, and I don't want us, honestly, everybody, right now, in trying to get us back on schedule, I don't want us to dwell on stuff with variables. That's not my point here, okay? When you take a look at something like B, we have negative 1 root 32 times 7 root 2. So what do I mean when I say we multiply coefficients by coefficients? I mean we can multiply the negative 1 by the 7, and radicals by radicals means we multiply root 32 times root 2. The negative 1 times the 7 gives you negative 7. The root 32 times the root 2. How do we multiply radicals? We multiply the radicands. So we still have a square root, but the radicand will be 2 times 32. And in this particular case, man, oh man, I'm off to a good start today. In this particular case, 2 times 32 is 64, and root 64 is 8. It's something that we often forget to do. You start getting caught up in, what's a number that divides into 64 that's a perfect square? Well, check to see if 64 is a perfect square before you even begin. Root 64 is 8, so we get negative 7 times 8. In order for you to be moderately successful at what was taught to you by myself on the video Thursday and Friday, this should be pretty straightforward. Not necessarily always easy, and for that reason, does anybody have any questions you would like me to go over? So take a moment and look at your work and see if you have any questions from page 289. Go ahead, McKenna. For D, 6 cube root 2 minus 4 root 13 quantity squared. Okay. So the thing is, if you had A minus B quantity squared, we have learned that you have to take A minus B times A minus B. You cannot, and I'll make this abundantly clear, you cannot do that. You cannot just square both pieces. You can do that if you're multiplying A and B, but not if you're adding or subtracting. So we have to rewrite. We don't have to. You might be able, and other people might be able to do this without rewriting it times itself, but I'm going to. 6 cube root 2 minus 4 root 13 multiplied by 6 cube root 2 minus 4 root 13. I think I can get rid of this. Does that make sense so far, McKenna? Okay, so now I have to FOIL. So the only thing that really makes this a Unit 5 problem in Math 20-1 is we've got radicals instead of just x's and numbers. So I'm going to multiply my first, and then my outer, and then my inner, and then my last. My first will be the product of 6 cube root 2 times 6 cube root 2. So I multiply the coefficients, and I multiply the radicands. So I get cube root 4. My outer is 6 cube root 2 times negative 4 square root 13. So I can multiply the coefficients of 6 and negative 4 to get negative 24. And then I can multiply the radicands as long as they're the same index. And the fact that one of them has a cube root and one of them is a square root is those things are as different to each other when we multiply them together as x and y are when we multiply them together. When you multiply x by y, all you do is you write xy. When you multiply cube root 2 times square root 13, you get cube root 2 times square root 13. And then my inner, well, my inner is going to be the same product because the binomial is being squared. So you're going to have another minus 24 cube root 2 root 13. And my last is negative 4 root 13 times negative 4 root 13. So negative 4 times negative 4 is 16. And it's been a while since I've been teaching this. I forget exactly how I did it with you. But root 13 times root 13 is root 169. But that's 13, right? So I'm pretty sure I have really tried to drill into our heads that this is always the case. And if it were a cube root, you would need 3 of them. So we're almost done here. I guess I should write 36 cube root 4. And then I can go minus 48 cube root 2 root 13. Because I have minus 24 of them and another minus 24. And by the way, some of you might be wondering, could you do this? And the answer is yes. The order that you put those two radical pieces together doesn't matter. And then I have, oh my goodness, 80, 100. 272. Okay. And that you can't really do anything else with that. We're done. You know, again, I don't want to get buried in cube roots and stuff, but could we break 4 into perfect cubes? No. Yeah.
I think the 17 should be 13.
17 should be 13? Where did I get 17 from? Oh, my goodness. Yeah. Thank you, Ollie. 13, that's 160, and 48 is 208. Thanks for that catch. Did I just say 208? Is that okay then? Is that what you were kind of wondering about too? Yeah. You're welcome. Other questions from that section? All right, so now we're going to move on. We're going to take a look at from Thursday's lesson. And the video, I tried to keep the videos as tight and short and compact as possible, just to the point, which is easy to do if I'm standing in a room by myself. It's not like I can ask you questions, but you should have had sufficient time. I know I said in this video and the one from Friday, well, maybe we'll have Monday as just a work day. I think we're going to move on today. I think you had sufficient time to work and figure out most of this. Again, I'm not saying it's easy. So you're going to have questions, but that's what we're going to do right now. What we learned on Thursday's lesson is that when you divide, you have the same set of rules. You divide coefficients by coefficients and radicals by radicals. So when you take a look at something like G here, G is, everybody, is almost too simple for an exam question. There's 25 over 5 is 5. Root 88 over 8, well, 88 divides by 8 11 times, so it's 5 root 11. And all of these ones, at least in question 1, all of the radicals divide, what's the word, nicely. Root 42 divided by root 6 is root 7, because 6 goes without remainder into 42. However, when you start to get to, and the same with here, these are just higher degrees or higher indices. When you get to stuff like this, like let's look at, doesn't matter which one we pick. I don't think 8 divides into 150, does it? Well, I mean, it does, but without a decimal? I don't think so. I think it's the same as 75 over 4. Am I alone here on this thought? So think about this. This divides into root 75 over root 4. And, you know, I'm not saying you can't do this. There's nothing wrong with you taking taking 150 divided by 8, seeing what you get, putting it into decimal form. There's nothing wrong with that. You know, the next unit's going to be challenging if that's the only way you can do it. Anyway, we kind of lucked out here because root 4 is 2. So I end up with 2 root 75 over 2. This is a coefficient because it's not under the radical sign. This is a coefficient because it's not under a radical sign, so they cancel. You're left with root 75, and now we are back to Wednesday's class, where you have to simplify that. Actually, not even Wednesday's class, Tuesday's class of last week. So this is root 25, root 3, 5 root 3. If we take a look at, I'm going to pick on now this one. Does 24 over 162 reduce down? In other words, we're going to divide the radicands, and they definitely reduces down. 12 over 81. Don't let me do all the math. 12 over 81, I think, can divide the top and the bottom by 2. Well, we lucked out again here because root 81 is exactly 9. So sometimes, you know, the math gods shine down on you. We're left with 18 root 12 over 9. Oh, 18 over 9. I don't feel like walking over to the highlighter side of the board. 18 over 9 is 2. So you get 2 root 12. How many of you know root 12 is 2 root 3? How many of you don't necessarily know it, but you can see it just by working it out in your head? You're starting to, it's like in the matrix. You're starting to see the matrix. You're starting to see beyond things that you have to write down on paper. Anyway, not everybody is capable of doing that, so we're going to write this as root 4 root 3. This is 2 times root 3, so it's 4 root 3. So what was different about this? Well, what was different, and I'm going to go to something like this. What's wrong with that? Can we divide the coefficients? No. Well, we can, but not without decimal. There's no radical on the top, but what's wrong? What's the golden rule here that you learned partway through Thursday's lesson and continued with Friday's lesson? Jack?
You need to rationalize the denominator by timing it by the congruent.
That's Friday. If it's a binomial, it's called the conjugate. We multiply the top and the bottom by the conjugate. Here, you're going to rationalize it by multiplying the top and the bottom by root 6. And by the way, you shouldn't have to be told to rationalize it. So if this question just said simplify, you should know that it has to be rationalized. So now what we're going to get is on the top 2 root 6. On the bottom 5 times 6, because root 6 times root 6 is 6. So we get 2 root 6 over 30. Well, now we have a coefficient and a coefficient, which can be divided. 2 over 30 is 1 over 15. So you get root 6 over 15. So when you have a monomial, and we'll get to the conjugate thing in a bit, Jack. When you have a monomial, you multiply top and bottom by that monomial. Does anybody have any questions from this lesson that you would like me to go over? No? All right. Finally, and I would describe everything that we're doing here as math that you know what you have to do. It's just the execution of it is sometimes challenging. You know what you need to do here. Following through with it and getting the right answer is where the tough part of the ride is. So when you have a binomial denominator, so for example, I'm going to pick on number f here, Jack, and in f we have root 2 over root 6 plus root 2. You multiply the top and the bottom by the conjugate of the bottom, which specifically in this case, well, I'll just do this over here. These are conjugates. A plus B, A minus B. Diamond plus heart, diamond minus heart. And the order that I write them in doesn't matter. So what is the conjugate of root 6 plus root 2? It's root 6 minus root 2. We multiply the top and the bottom by that conjugate. So why do we do that? We do that, and I know this was in the lesson, but I want to review it. Because if you FOIL out the bottom, your outer term will be negative root 12. Your inner term will be positive root 12. They don't exist in the product. So as I said, kind of flippantly, when you have conjugates, you don't need to FOIL, you just FLA. That's all you have to do. So I take root 6 times root 6, which is 6, minus root 2 times root 2, which is 2. Well, it doesn't get much simpler than 6 minus 2. Well, it does, 4. On the top, we have to multiply this out. So I'm going to get root 6 times root 2, which is root 12, minus root 2 times root 2, which is 2. So what does that give us? Root 12 minus 2 over 4. Am I allowed to do this? No. Why not? Because I can't cancel a 2 unless 2 is a factor. This is so important for the next unit. That 2 that I cancel has to be in brackets times everything else. Can I do this? Well, that's even crazier, because one of these is a radical and one is a number. So never go there. But we're not done until everything is simplified, and you can simplify root 12. Root 12 is 2 root 3. There will come a time where I will stop writing that. There will come a time, there has to be, where I just say, geez, we've done root 12 100 times. It's not going to be something different than it was yesterday. It's 2 root 3. What else do we have? We have minus the 2, and then we have over the 4. Lily, can I cancel anything here? Yeah, I can cancel as long as I cancel the 3 of them. That's what you meant by the 3, right? I can cancel as long as, so this is just what we were talking about with the quadratic formula, the same thing. As long as I cancel out of all 3 coefficients, it will work. The reason for that is if I factor a 2 out of the numerator, I'm left with root 3 minus 1. It's over 4. Well, now we have coefficient over coefficient. The 2 on the top and the 4 on the bottom cancel, leaving me with 1 over 2, which is what you would get if you did this. You'd get root 3 minus 1 all over 2. And that is as simple as it gets. That's the answer. So now take a look at your work in that final section and see if you have any questions you would like me to go over. And again, it's the execution here that's the hard part. You know what you have to do. Go ahead, Sasha. 2a? Certainly. So we have 2 root 3 over 3 root 2 plus root 3. And I'll tell you what I think makes the execution here difficult is you've got roots, you've got not roots, you've got 2's, you've got 3's. Visually, it's a bit of an assault on our senses. But I'm going to multiply the top and the bottom. This is the one you asked about, right? Okay, good. I'm going to multiply the top and the bottom of this expression by the conjugate of the bottom, which is 3 root 2 minus root 3. And I don't remember when this happened. I want to say it was when I was still here on maybe Monday or Tuesday of last week, or I can't remember. But there was some problem we were working on, and I made a big point of saying, don't multiply out the top. Leave it in factored form so we can cancel. We're not following those rules anymore, not with this. You have to multiply everything out to see what's going to happen. So when I multiply out the bottom here, Sasha, I'm going to get 9 times 2 minus 3. So that's my FLA. If I multiply 3 root 2 by 3 root 2, the 3 times the 3 is 9. That's where my 9 comes from. The root 2 times the root 2 is 2. How many of you have graduated to the point where you just write 18? You see it and you go 18. Again, be careful. And then do you see where I'm getting minus 3 from? Root 3 times root 3. Well, root 3 times negative root 3 is negative root 9 or negative 3. On the top, be very careful. I'm going to multiply this by this, right? I have to do that. And that is going to give me 2 times the 3, this extends over to here. 2 times the 3 is 6. Root 3 times root 2 is root 6. Okay. Then I have to multiply the 2 root 3 by the negative root 3. There's really a 1 there. So when I multiply the coefficients, I take this 2 times this negative 1 and get negative 2. And then root 3 times root 3 is 3. One of the biggest mistakes that people make, and it's just I think it's your brain trying to cope with everything that's going on, is you mix up from time to time multiplying this and multiplying this. I see it all the time. I see people going root 3 times root 3 and they write the number 9 down. It's not 9, it's root 9, which is 3. And I also, this is weird, I also sometimes see people go 3 times 3 and then they say that's root 9, which is 3. But 3 times 3 is 9. So be very careful about what has roots and what doesn't. What do we get on the bottom here? On the bottom we get 18 minus 3, which is 15 by my count. On the top we get 6 root 6 minus 6. Can I do any canceling? Well, as Lily said, and I've said numerous times, in this situation where you have a binomial on the top and a monomial on the bottom, you can cancel coefficients as long as you don't play favorites. Every coefficient gets slashed by a factor of 3. So if I divide 6 by 3 and 6 by 3 and 15 by 3, I get 2 root 6 minus 2 all over 5. Is that okay? Perfect. Other questions? Go ahead, Zoe. 2c and anything from 3. Certainly. So 2c is root 2 over root 12 minus root 8. Now, there are 3 problems with this that need to be resolved to simplify. One is root 12 can be simplified because it can be broken down into root 4, root 3. Root 8 can be simplified. The other problem is we don't want radicals in the denominator. So you have an option here, Zoe. Everybody, you have an option. We can simplify that root 12 and the root 8 first and then multiply the top and the bottom by the conjugate, or we can do it later. It doesn't matter. You can't run from that. It's going to be there. Do you have a preference? Okay. I might be inclined, and I think this might have come across in one of the lessons that I recorded, I am a fan of simplifying radicals first. I think it makes it easier for me. So what I've done is I've said, well, what is root 12? It's root 4, root 3, and root 4 is 2. 2 root 3. What is root 8? Root 8 is root 4, root 2, and root 4 is 2, so it's 2 root 2. Now, can I cancel anything? Boy, that would have been nice if I could, but I can't. Look at your coefficients. 1, and I'm going to move this root 2 over a little bit. 1 root 2, 2 root 3, 2 root 2. Those 3 coefficients don't have anything in common. Okay? And by the way, I won't even go there. So we can't simplify anything else yet. Let's multiply the top and the bottom by the conjugate of the bottom. So I'm going to multiply top and bottom by 2 root 3 plus 2 root 2. And because I've mentioned this a couple of times, the difficulty lies in the execution. You need to go slow. You need to double check to make sure you've written roots where there are roots, numbers where there are numbers. I think it looks okay. I'm going to multiply out across the top and get 2 root 6 plus 2 times 2. Zoe, I want you to think about what I did there and see if that makes sense to you. Okay. On the bottom, I don't need to FOIL, I just FLA. So I take 2 root 3 times 2 root 3. 2 times 2 is 4. Root 3 times root 3 is 3. Minus 2 root 2 times 2 root 2. The 2 times the 2 for the coefficients is 2. The root 2 times the root 2 is 2. You know, I almost wrote 4 there. I almost wrote 4. You could even see that line coming down on the 2? I was going to write 4. It's such an easy mistake to make. Are you okay with that? Okay. So now what do we get on the top? 2 root 6 plus 4. And it's at this point in time that a part of my brain is starting to go, well, look at this. The coefficients are both even. So I'm already looking ahead to the bottom, hopefully being an even number. I have 12 minus 4, which is 8. And it is even. So I can divide all of those coefficients that I've highlighted by the same number, which is 2. 2 root 6 over 2 is root 6. 4 over 2 is 2. 8 over 2 is 4. So that's our answer. Perfect. Anything from 3? Well, strangely enough, you might think that this will be the more difficult one, C, because it's all radicals. But where it gets confusing if it's a mixture of radicals and numbers. So I'm going to tackle D. I cannot simplify root 10. There's nothing I can do with root 10. So the only thing I can do here with D is rewrite it and multiply the top and the bottom by the conjugate of the bottom, which will be 3 minus root 10. Does that make sense? Okay, so that's the rule. If it's a monomial, one term in the denominator, you just multiply the top and the bottom by that radical. So if it's 5 root 8 on the bottom, multiply top and bottom by root 8. I'm going to have to FOIL out the top. And I'm going to have to FLE the bottom. So when I FOIL out the top, 5 times 3 is 15. Outer will be 5 times root 10, which is 5 root 10. Inner will be negative root 10 times 3, which is negative 3 root 10. And then it's plus 10. Are you okay with that? Okay. I hope you see a similarity here between what we just did and foiling out something like this. You get that negative 5x, you get that negative 3x. On the bottom, what do we have? Well, 3 times 3 is 9. Root 10 times root 10 is 10. So we get 9 minus 10. Simplifying the top, 15 plus 10 is 25. Plus, do you see how I'm getting 2 root 10? Okay. It's over negative 1. I'm actually glad I picked this. I didn't know this was going to happen. I'm getting my classes mixed up. If I had a fraction of a over b and it was negative, I think you know that I really don't like putting the negative there. Because, what do we do with it mathematically when you're working with fractions? It's kind of weird. I think you know that even less is this idea. I don't like that at all. I prefer this. There's a slight problem here, that if I put that negative 1 on the top, I don't have to write over anything, first of all. And I can just write this. But this is wrong, isn't it? What's wrong with it? Do you know, Zoe? Anybody know? Kai? Yeah, it's the negative of the entire top. So you either need to write that, or, as Kai pointed out, and really what you're doing here when you do that, and some of you might see it this way, is you're reducing all of the coefficients down by a factor of negative 1. Anyway, that's 3D. Is that okay? Any other questions before we get started today? Go ahead, Sasha. 5C. Root k plus root 2 over root k minus root 2. All right, here we go. So we are going to have to multiply top and bottom by root k plus root 2. Not because that's what's on the top, but because that's what the conjugate of the bottom is. So we're multiplying the top and the bottom by the conjugate of the bottom. So on the bottom, we're just going to have fla, which will be root k times root k minus root 2 times root 2, which will be k minus 2. On the top, I have to FOIL that out. So root k times root k is k. My outer is plus root 2k. Because I have, if I had root 2 times root 3, that's root 6. I multiply the radicands. So when I am multiplying this by this, I need to multiply the radicands. K times 2 is 2k. That's why I get root 2k. Are you okay with that move? Okay. My inner will be identical to my outer. This is an interesting thing that I didn't really bring to your attention, but you talk about in 10C. When you multiply two binomials that are identical, your outer and inner are the same. So you get two of them. When you multiply two binomials that are conjugates, your outer and inner are opposite, so you get none of them. Right? That's why we don't have an outer and an inner here. And then I also have root 2 times root 2, which is 2. And there's really not much you can do with this at this point, Sasha. We have a k. We have 2 root 2k's. We have a 2, and then it's over k minus 2. And you cannot simplify anything there. If you wanted to simplify this, the only way you would be able to simplify it is if this, and this all had some number you could cancel. Every coefficient needs to be included. You cannot treat some coefficients differently than others. Is that okay? Other questions? Okay, so we are going to get started on the next lesson today. I don't know how far we're going to get. I suspect that tomorrow will be a work day. I would rather come back and do what I just did for half the class and then teach you something new, then have a work day, than to just come back and say, well, let's just practice. Okay? So we're looking at the next lesson, which is section, I believe, 5.3. And we break section 5.3 down into two parts, part 1 and part 2. Apparently this is on page 13 of your unit handout. Does that jibe with what you've got there? Okay. All right, so we're going to be solving radical equations. And this bit of business here, this is the first thing we're doing. This bit of business about extraneous roots is something new to you, I think. Yeah. A root, we learned this in, the last unit for sure, maybe even before then. A root of an equation is a solution to the equation. So what does a solution to an equation mean? It means it's a value for the variable that makes the equation true. Let me tell you what an extraneous root is. An extraneous root is a solution to an equation that you get by doing the math perfectly, but the answer you get is wrong. You do everything right, you follow all the rules, but when you take that value of x that you find and you put it into the original equation, it is not a solution to the equation. It's a very strange thing, and it pops up in a number of areas in math, a couple of units this year and a couple next year. So let's start off with how we solve a radical equation. Everybody here should know by now that I'm a huge fan of taking a math problem at one level and turning it into a math problem at an earlier level. We can take a math problem that's a grade 11 math problem and turn it into a grade 10 math problem. That's good. If we can take a math problem that's a unit 5 math 20 problem and turn it into a unit 3 math 20 problem, that's good. So how do we do this? Let me first of all show you. This is a radical equation. Don't worry about anything else or doing this example or anything like that. This is a radical equation. Why? Because it has a radical in it. So there is a radical right here. And because that radical is there, you don't know how to solve it. Okay? There's a radical here. Well, you don't know how to solve these. You do not know how to solve these equations yet. That's what we're going to teach you right now. There's a radical here. Don't know how to solve it. There's a radical here. No idea. Two radicals. You cannot solve an equation with radicals. So what these steps are designed to do is to get rid of the radical. If you can get rid of the radical, you turn the equation into an equation from earlier math. So how do we get rid of the radical? You isolate the radical term, which means rearrange the equation so that that term is by itself on one side, and then square both sides of the equation. Before we get to number 3, let's do that for this particular question. So we want to isolate the radical. Well, that's pretty easy. I'm going to subtract 5 from both sides, right? I mean, I didn't show that, and I think another thing you know about me by now is I'm not really a fan of having to write this every time, particularly with numbers like 5, but there you go. That's step 1. Step 2, square both sides. Remember, an equation is still valid whenever you perform the same operation to both sides. That's why I can subtract 5 from both sides. I could multiply both sides by 1,000,000 if I wanted to. I could add pi to both sides, or I could square both sides. When I square the left-hand side here, I get 2x minus 1. Because the square of a square root cancels. We've talked about this before. One way I can show that to you is to say that root 2x minus 1 squared means root 2x minus 1 times root 2x minus 1. And we know that root 17 times root 17 is 17. The squaring or the multiplication of the radical by itself gets rid of the radical. And then 7 squared is 49. Oh, okay. Grade 5 question. Grade 3 question, maybe. Sharp grade 3 student, right? Not all of them. We've seen grade 3 students. They're not all there yet. But if I add 1 to both sides and divide both sides by 2, it's child's play. So I add 1 to both sides. I get 2x equals 50. So then I divide both sides by 2, I get x equals 25. So, but step 3, if you look at your notes, step 3 says check to see if it works. It says check to see if there are any extraneous roots. Extraneous roots must be disregarded or discarded. So what is an extraneous root? I've already told you. It's a number you get for the solution that is not a solution. So how can we check to see if this is a solution? Our equation was 5 plus root 2x plus 1 equals 12. When you check, you do not put equals. Yeah. Thank you. Root 2x minus 1, thank you, Ashlyn, equals 12. When you do your check, it's called a left side, right side check. You do not use the equal sign. What you do is you put your number in for x on both sides, and if you get the same result on both sides, then it's a valid solution. So 5 plus root 2 times 25, and then minus 1. There's nothing to do on the right side. It's just 12. So we get 5 plus the square root of 50 minus 1 is 49. 5 plus 7 gives you 12. Jackpot. It works. And I know that some of you are going, why wouldn't it work? Like, really, it's a good question. Why would you get an answer that's wrong if you did the work right? We'll see why in a bit. So what we do here, what I recommend you do is you put a check mark beside that answer to indicate that you've checked it and it's valid. Let's try another one. Well, we have to isolate the radical here. By the way, it does say, I guess we have one more thing to do here. It says state the restrictions on the variables. So this is a little bit different than what we did before with restrictions. But the radicand has to be greater than or equal to 0 because you cannot take the square root of a negative. Okay? So if I rearrange this, I can write 2x must be greater than or equal to 1, which means x must be greater than or equal to 1/2. That's the other part to this question. And that's the restriction on x. I would like to be able to tell you that it's very important, but it's not. Not for solving the equation, but for knowing how to find that restriction, particularly when you get to 30. I don't want to be in Math 30 with you and have to teach you how to find a restriction. I want you to have seen it already. Okay? There's a restriction on x. In terms of solving the equation, who cares? The solution's 25. Okay, let's isolate this radical. I'm going to leave the radical where it is. Root 3y over 5 equals positive 8 minus 2. What is that going to give me? It's going to give me root 3y over 5 equals 6, and I'm ready to square both sides. So what do I get? When I square the left-hand side, all I'm left with is 3y over 5, and when I square the right-hand side, I'm left with 36. It's not really a grade 3 question yet because there's fractions there, so let's multiply both sides of this equation by 5. See, making problems simpler. What's one way you can make a problem simpler? Get rid of the radicals. Square both sides. What's another way you can make it simpler? Get rid of denominators. Multiply both sides by 5. There's kind of a recurring theme here. I don't think you should memorize that if it's a radical, you do one thing, and if it's a fraction, you do another. Although that's helpful. What you do is you simplify it. You make things easier by doing the same thing to both sides of the equation. 5 over 5 cancels. So I'm left with 3y equals 36 times 5, which I think is 180. Am I right? Thank you. I divide both sides by 3 and get 60. And now I put 60 into the original equation and see if it works. So on the left-hand side, I will have negative 8 plus the square root of 3 times 60 over 5. On the right-hand side, I have negative 2. 3 times 60 over 5 is, I believe, 36. And the square root of 36 is 6. Negative 8 plus 6 is negative 2. Again, all is right in the world. That's a correct solution. Which, again, we're still on the edge of our seats here wondering why do we got to check? You'll see it in a minute. Any questions with number 2? Yeah. This one? Okay, so now we'll do the restrictions. The restrictions would be that radicand I'm going to get rid of this. And I'm just going to also say one more thing before I answer your question, Ashlyn. That checking part, if you're just working on your own and practicing, you don't need to show any of that work. But if it were a written response, you would want to have that as part of your solution. So now the restriction, which again is not that big of a deal in terms of today, you would say that the radicand must be greater than or equal to 0. We would multiply both sides of that by 5 to get rid of the denominator and get 3y is greater than or equal to 0. We would divide both sides by 3. By the way, when we multiply the 0 by the 5, it's still 0. When I divide both sides by 3, I'll get y on the left side greater than or equal to 0 divided by 3 is still 0. So the restriction would be y is greater than or equal to 0. Okay. But again, solving the equation and checking for extraneous roots is this today. It's way up here. That restriction on the variable is important for later, but it's kind of laying on the floor. It's not that big of a deal right now. Okay, let's isolate the radical. I would be tempted here, everybody, to move the radical to the right-hand side of the equation. Just like I don't like having negative x's, I don't like having negative radicals. So I'm going to add that radical to the other side, and then I will have n plus 7. Essentially what I did was this term, which is negative, I moved it to the other side where it became positive. This term, which is negative, I moved it to the other side where it became positive. I'm adding terms to both sides. So now we square both sides. What happens on the right-hand side is I get 5 minus n. And on the other side, I have n squared minus 49, or plus 49. Are you okay with that? I sure hope not. Am I allowed to take n plus 7 quantity squared and just square the n and square the 7? It's n plus 7 times n plus 7. I used to kind of joke that whenever anybody does what I just did, a kitten dies. Okay? But some people got really upset by that, so I promised myself I'd stop saying that, and in the process of explaining that, I just told you that a kitten died somewhere. So no kittens were harmed during the math of this. This means n plus 7 times n plus 7. We have to FOIL it out. You can't, that's what I would call a rookie mistake. You cannot make that rookie mistake in grade 11. That's a grade 9 mistake. You make it, it doesn't matter what you understand from this class, you make that mistake, it's wrong. So we're going to get n squared plus 7n plus 7n is 14n plus 49. Okay. We didn't turn this equation into a grade 3 question or even a grade 10 question, but we turned it into a quadratic equation question, which we do know how to solve. I'm going to zero this equation by moving everything to the left side. So I'm going to add n to both sides to get n squared plus 15n, and I'm going to subtract 5 from both sides to get plus 44. This happens to be factorable. As far as this goes, everybody, I don't think you're likely to see in this course a radical equation that turns into a quadratic equation where you have to use the quadratic formula. Okay? But next year, maybe. So this is factorable into n and n. What two numbers multiply to give 44 and add to give 15? That would be 4 and 11. That means n plus 4. Now comes the grade 3. N plus 4 equals 0. You got a really bright grade 3 student who understands negative numbers. N plus 11 equals 0. So n is equal to negative 4. N is equal to negative 11. Now before I finish this question, let's do the restrictions, okay? And this might be the last example we do, and I'll give you a few to practice for tomorrow, okay? Let's do the restrictions here. The restrictions would be found by saying 5 minus n must be greater than or equal to 0. It seems to me we've done this already somewhere. Have I talked in this class about the need to flip the sign when we divide by a negative? I can't remember when we did that, but we were doing something where we had an inequality and we had to flip the sign. So if you subtract 5 from both sides, you get this. When you divide both sides by negative 1, you're going to get positive n and positive 5, but you need to flip the sign. Okay? However, and I wish I could remember when we did this, that's not what I would do. I would instead, so you can do this, or I would move the n over and read it backwards. Does that ring a bell? Because if 5 is greater than or equal to n, then n is less than or equal to 5. Okay? And I'm doing this for a reason. One is next year you need to know this, but your textbook contains a huge, huge error. I can't believe it got past the publisher. What does n is less than or equal to 5 mean? It means that n can be any number equal to 5 or to the left of it on a number line. Are you with me? Is negative 4 to the left of 5 on a number line? Yes. Is negative 11 to the left of 5 on a number line? Yes. Here is the mistake, and I don't know if it was the author or the editor, the mistake that's made in your textbook. They claim that since both of those numbers are allowable values of n, they're both correct. They're claiming that if they're in that domain, they're correct. But let's check them. Remember, the third step says to check. So our equation is n minus, I'm going to go to a new page here, n minus root 5 minus n is equal to negative 7, correct? What was one of the answers we got for n? Negative 4? Okay, let's put negative 4 in. Negative 4 minus root 5 minus negative 4. Let's see. Negative 4 minus, let's see, what's 5 minus negative 4? That's 9. Root 9. Root 9 is 3, so we get negative 4 minus 3. Well, negative 4 minus 3 is negative 7. And that's what we're supposed to get, right? So we go back over here to our work. And it's valid. Let's try negative 11. Well, with negative 11, I get negative 11 minus, it's 5 minus negative 11 under the radical sign is 16. And root 16 is 4. This is negative 15. It doesn't match. We didn't do anything wrong. Some of you might figure out what happened here. But I'm not worried about why. I'm just telling you that it didn't work. So what we would say here, everybody, is that this is not a solution. That doesn't mean X. It means no. It's called an extraneous solution, or an extraneous root, or an extraneous answer. And it is just not an answer. I dislike calling it an extraneous solution. It's just not an answer. But see, your textbook claims that it is because it's in the allowable values of n, but that's not true. Which is one of the reasons why I said this thing is really not important in solving the equation. It's got nothing to do with the solutions to the equation. Well, let's do this one together, and then I'll give you a few to try for tomorrow. Okay? Then tomorrow will be a work day. I just have to rearrange the schedule for the unit to make that possible, but we'll be able to do it. So let's isolate the radical. I'm going to subtract 6 from both sides and move that radical, which is negative, to the other side. Then I'm going to square both sides. And I would like everybody to take a minute and write out what we're going to have after you square both sides. And by the way, the whole restriction is so unimportant, I'm not even going to do it for this one. Yeah. No. So let me, I don't think, and it's, I'm not trying to be cynical, but math is hard. Like sometimes it's just, you see things in a way that are not right, but you convince yourself they are. And that's myself included. And that's the reason I'm saying this is I want to double check because maybe it is, but I don't think it is. So I want to rewrite this as positive m minus root 2m plus 3 equals positive 6. So if you look at what I did, I have on the right-hand side the root. I think you see it now, but I'm going to finish it. I'm going to finish my explanation. So I accomplished that, Will, and everybody, by adding this to both sides. So I end up with just m over here equals 6 plus root 2m plus 3. So when I subtract 6 from both sides, I get minus 6. And that's a hazard we face when we take shortcuts. The shortcut, of course, is not to write plus root 2m plus 3 plus root 2m plus 3. But having to write all that all the time sometimes is worth the risk because it's a big time saver. Not writing it is a big time saver. Anyway, we're okay with that? Well, okay. So don't forget m minus 6 times m minus 6 is m squared plus minus 12m plus 36. I can zero this equation. M squared minus 14m plus 33. How is my addition and subtraction there, okay? All right. As I said, in this section, these will all be factorable if you get a quadratic. In this case, it's m minus 11, m minus 3, two numbers that multiply to give 33, add to give negative 14. So m is equal to 3, and m is equal to 11. Because you go m minus 11 equals 0, m minus 3 equals 0. And then, because this is our final example we're going to do today, I'm not going to write this down. Let's put together 3 into the equation and see if it's true. So I put 3 here and here. I want you to figure out if you get 6. I believe you'll get 0, won't you? Because you'll end up with 3 minus root 9, which is 3. 3 minus 3, yeah, is 0. 3 is out. We knock 3 over the boards. It's an extraneous root. Again, you know me, if it's a written response, you better explain that or demonstrate that it's not a valid solution. 11, we put 11 in. We put 11 in here and here. Let's see, I will have 11 minus, what's 2 times 11 is 22, plus 3 is 25. So we get 11 minus root 25. Root 25 is 5. 11 minus 5 is 6. Works. Again, you know, I will do the restriction. The restriction would be arrived at by saying, since 2m plus 3 is under the root sign, 2m plus 3 must be greater than or equal to 0. But again, and this is tricky. This restriction that I'm not done yet, that I'm working on, has no bearing on the answer to the question. It's got nothing to do with it directly. It's got something to do with it that you'll learn about next year. So if I subtract 3 from both sides, I get this statement. Divide both sides by 2, I get m is greater than or equal to negative 3/2. Both of these numbers are greater than or equal to negative 3/2, but that doesn't make them solutions. You have to manually check them. 3, 4, and 6. 3, 4, and 6 is your assignment. This stuff, this is what I describe as parsley on the fish. It doesn't mean anything. It's just the restriction. Who cares about it? If you want to ignore that, you can. So 3, 4, and 6. Question 3 and 4, so simple. Square both sides. Well, isolate the radical. If you look at a, root z equals 5. I've isolated the radical by subtracting 8 from both sides. I'm done. Z equals 25 because I square both sides. I can check to see if it works, and it will. Anyway, 3, 4, and 6. That's your assignment for tomorrow. It's not just practice. I want you to do all of it. Tomorrow we will finish this lesson and have a global practice of everything so far.